Hello everyone and welcome. We're going to do some binomial hypothesis testing for the next 2 weeks in class. So this is the first of 6 lessons where we're going to approach this topic. So today the idea is we learn what a hypothesis test is, how we can use the binomial distribution to conduct a hypothesis test, and also what we mean by terminology like significance levels, critical regions or critical values. So here is a binomial distribution question that we're quite familiar with up to this point. We have a pharmaceutical company claims that 85% of patients suffering from a chronic rash recover when treated with a new ointment. A random sample of 20 patients with this rash is taken from hospital records. Write down a suitable distribution to model the number of patients in the sample who recover when treated with the new ointment. Now that's pretty standard stuff. We know that this is going to be a binomial distribution, so we'll use X, and we've got B for binomial. We know that it's binomial because we have a number of patients. We have a sample of 20 patients. That's a number of trials, and the probability of success is this 85%. 85% of patients recover. Okay, so there's a success and a fail criteria. Okay, success is that they recover, fail is that they don't recover. 85% chance of recovering, 15% chance of not recovering. So it fits our binomial distribution pattern. So there's our distribution, and that's it, right? Write down the suitable distribution. That's all we've got to do, right? So for part B, given that the claim is correct, find the probability that it will be successful for exactly 16 patients. So this is test statistic X equals 16, and we work this out by using our NCR calculation. So we have 20 choose 16 multiplied by 0.85 to the power of 16 multiplied by 0.15 to the power of 4. And we can evaluate that pretty quickly and get our answer. Should have got my calculator ready. Right, so 20 C16 multiplied by 0.85 to the power of 16 multiplied by 0.15 to the power of 4. So we have a probability here of 0.1821 to 4 decimal places. So all of that is stuff that we know how to do. Okay? There's nothing new there whatsoever. However, have a look at the second part of this question. The hospital believes that the claim is incorrect and that the percentage who will recover is lower. From the records, an administrator took a random sample of 30 patients who had been prescribed the ointment. They found that 20 had recovered. Using a 5% level of significance, find the critical region for this test and determine whether the hospital's belief is correct. Now you can, think about that situation as a real-life situation. It seems perfectly reasonable. A hospital believing that the claim is not correct. How do we test that? Well, that's the job of hypothesis testing. We've taken a sample of 30 patients in this instance, and we found that 20 had recovered. So there's this kind of subjective judgment going on here. Is 20 out of 30 representative of the 85% that recover when they're treated with the new ointment? I mean, 20 out of 30 is around about 67%, isn't it? So it seems to me like it's quite a lot less than 85%. But then who am I to judge that that is significantly lower and therefore your claim is rubbish? I have no real evidence. I just have my opinion. Someone else's opinion might be that 67% is actually quite close to 85%. And, if it had been perhaps below 50%, then I'd be worried. So this idea of defining what constitutes a significantly different outcome is the heart of binomial hypothesis testing. So we've got some interesting language going on here. We've got a 5% level of significance. Now, this is something that you will see in every question that you do, and you will typically work with 5% levels of significance, 1% levels of significance, or 10% levels of significance. Okay, they tend to be the most common ones that we'll see. Now, what does it mean by a 5% level of significance? What this means is the conclusion that we make at the end of this process is only going to be wrong 5% or less of the time. Okay, so we are working with probabilities. Nothing is certain, but that, just to get that kind of really clear, we're saying that the conclusion we make at the end of this will be wrong less than 5% of the time. Now, I'll let that sink in a little bit. So then we're going to find this critical region, and a critical region is really important for hypothesis testing. It's the region that returns a significant result. It's the boundary. So in this example here, we're testing whether or not this 67% is significantly lower than the 85%. So when we find the critical region, we're finding that boundary percentage. What number is sufficiently far away from 85% so as to mean that this result is actually significant? And this is where we take any subjectivity out of what's happening. We're just saying that, okay, we have a definite value that cannot be argued with. Anything below that value is significantly below the 85%. That's what we're trying to find. So here's how we do it. We have our distribution as before, but this time we have a random sample of 30 patients. And we have this probability that we are testing of 0.85. Right? So this is a new distribution simply because we've changed the number of patients to 30 that we've taken a sample of. So 30 patients, 0.85. We have to state our hypotheses clearly. All right? It doesn't actually say it in this question, but this is what we always have to do. Now, when we're hypothesis testing, we have two hypotheses. We have H0, and that is called the null hypothesis. The null hypothesis is there's nothing to see here, everything's fine, the percentage is as the company claims. So the null hypothesis, when we're dealing with a binomial hypothesis test, is always that the probability is what it says it is. Now, so this is always the same. For our binomial tests, H0 is always P, meaning probability, equals the probability given in the question, in the distribution. Now, opposite to that, we have what's called the alternate hypothesis. And this is the hypothesis that actually, no, that percentage is incorrect. And so we have to describe that in terms of the probability. So the alternate hypothesis is, yeah, do you know what? Something's different. We want to test that. And for this problem here, because we've established that 20 out of 30 is below 85%, we're testing that the probability is actually less than 85%. So our alternate hypothesis is saying, no, the probability is less than 0.85. You always state the distribution. You have to state the null hypothesis. You have to state the alternate hypothesis. The null hypothesis is always P equals the value here or given in the question. And the alternate hypothesis is always from the question. And by that, I mean, this is a less than question because 20 out of 30 is less than 85%. It could be a greater than question. We're going to look at those tomorrow. And it could be just a not equal to question. We're going to look at those next week. But for today, we're always going to be looking at less than probabilities. So the next thing I'm going to write down is my significance level is 5%. And I'm going to write down that this test is actually one-tailed. Now, you don't get marks for either of these bits of information. This is just to keep me on track. It's something I always add into my work. If you're wondering what a one-tailed test is, it's very difficult to describe without going into what two-tailed tests are, and we will do those next week. So just don't worry about this one-tailed aspect for the moment. So we want to find this critical region. This is us. We've set up our hypothesis test mathematically. Now we get to the business of finding the critical region. Remember, this is what probability or what value out of 30 patients, how many would have to recover in order to be considered significant or not significant. Okay, so that's what we're going to get to. Excuse me for a sec. Sorry, someone just came in. So what we're interested in actually is how many would you expect out of this sample of 30 patients to recover? And to do that, we're going to calculate what's called the expected value. Now, we did touch on this when we studied the binomial distribution the first time around. You may or may not remember it. It's not in the specification, but it is a very useful piece of information. The expected value of x, in this case, stands for how many out of 30 would you expect to recover if the 85% is true. So we take the 30 and we multiply by 0.85. And we would expect 25.5 patients to recover if there was an 85% success rate. Obviously, you can't have 25.5 patients, but we do leave that because it is the mean, so we leave that unrounded. But this, again, isn't part of the marks. It's just giving us a starting point. And what I tend to go for is I tend to choose maybe 2 below the expected value to start testing for my critical region. And this is what I mean by that. So I'm going to test what's the probability of x being less than or equal to 23. Again, I've just used this as a starting point and I've gone a couple below that. So what's the probability that x is less than or equal to 23 in this distribution? And if you're wondering what we're doing here, it will become clear once we've worked this out. So we've got menu 7 on the class whiz. We're going to scroll down. Binomial CD, variable. Our x value is 23, our n is 30, and our p is 0.85. So we have here the probability of 0.1526 to 4 decimal places. So the probability of there being less than or equal to 23 patients out of the 30 who have recovered is 0.1526. Okay, so there's a 15.3% chance that less than or equal to 23 out of 30 would recover, okay, which is quite small. Now, what we are looking for is actually a value that's less than 0.05. Once we get a probability from this that is less than 0.05, which comes from the significance level, that is our boundary. That is the number that makes a significant result. So at this point, 23 patients out of 30 isn't significantly lower than 25.5 to create any concern, because the probability of that happening is 0.15. We need to keep going until we find a probability that is less than 0.05. So let's test the next value down. Remember, we're going to try and get further and further away from this expected value in order to test to find our probability. So x is less than or equal to 22, n is 30, p is 0.85. This time we have 0.0698, again to 4 decimal places. And we check this. So 0.0698, certainly getting closer to 0.05, but it's not below 0.05. All right, so 22 is not a significant result. We keep going. And this is a case of trial and improvement. We'll learn a faster way to answer some of these questions in the 3rd lesson, but for now, we're using trial and improvement. So we'll go x is 21, and we get 0.0278, again to 4 decimal places. And finally, we have a value less than our 0.05. So what we're going to say here, and in the context of the question, this means that a number of patients recovering of 21 or less out of the 30 is evidence that the 85% claim is incorrect. All right, I'll just repeat that. If we have a result of 21 patients or fewer out of the 30 who recover, then the 85% claim is incorrect. Now, here's how we summarize our conclusions. We say two things first. The critical value is X is 21. That's the boundary. That's the point below which everything becomes significant. The critical region is X less than or equal to 21. So we've been asked for this critical region. So the critical region X is less than the 21 means that any result out of 30 patients that is less than or equal to 21 is going to be significantly lower than 85%. So now we're going to test our value. We found that 20 had recovered. So we say 20 lies inside the critical region. Okay? So when we say it lies inside the critical region, it means that it is less than or equal to 21. And then we make two conclusions. The first conclusion, and this is the language I want you to get used to using, is that there is sufficient evidence to reject the null hypothesis H0. So you're going to make two conclusions here. The first one is always whether or not you can reject the null hypothesis. So the null hypothesis, remember, is that the probability is 0.85. We're saying that we have sufficient evidence here to reject that hypothesis. The second conclusion has to do with the context of the question. And so we say that there is evidence that the company's claim is incorrect. And that's the question done. So there's a lot going on there. You have to trust me that this is not a difficult process. It's always the same process, but it does rely on your intimate understanding of what's going on. So just to kind of recap, we were told this information about an experiment. We had 20 out of 30 patients have been prescribed the ointment, who had been prescribed the ointment have recovered. We noticed that that was below 85%, and we are testing the claim that actually that 85% isn't true. So in order to test that, we have a null hypothesis saying that it is true. We have an alternate hypothesis saying that it's not true. In fact, it's less. We have a significance level, which allows us to say our conclusion is accurate 95% of the time. Okay, there's a 5% chance that our conclusion here is wrong. That's what this means. How we use the significance level is we test some probabilities until we find one that is less than the significance level. As soon as we found a probability less than the significance level, we have our critical value, meaning below this number, everything is significant. So we got 21. Our critical region, therefore, was less than or equal to 21. We compared the 20 people who had recovered out of 30 in the question with this result. 20 is less than or equal to 21, so it's inside the critical region, which means that we reject the null hypothesis. This does not seem to be true. And we say that there's evidence that the company's claim is incorrect. Okay, so let's have a look at a second example. So here's our second example. Previous research by a restaurant found that 30% of customers will order a starter. One day, a random sample of 40 customers is taken and 7 order a starter. So before you even get into the question, let's just have a think about that. 7 ordered a starter out of 40. Does that seem to be less than or greater than the 30%? Seems to me it's going to be, that looks less than 30%. Okay, that's what I'm thinking. So test at the 5% significance level whether the proportion of customers ordering a starter has decreased. Now don't worry about the fact that we've skipped out part A here. There would have been a reason for that. Okay, so let's start off the question as we always should do. We're going to use a binomial distribution, and that's because we have a sample size, a number of trials, and we have a probability of success, which is the probability that was established in the question. So here we have 40 and 0.3, which is our 30%. We need to write down our null hypothesis and our alternate hypothesis. So H0, I forgot to mention in the last one, that's a 0. So H0, the null hypothesis, is that, yep, the probability is 0.3. The alternate hypothesis is that the probability is less than 0.3. And we get that less than because 7 out of 40 seems to be less than 30%. So our expected value, which is another useful piece of information, would be the 40 multiplied by 0.3, which is 12. So we would expect out of a sample of 40 that 12 would order a starter if the 30% probability is correct. And we've got a 5% significance level, and we have a one-tailed test. Again, don't worry about the one-tailed thing. We'll come back to that next week. So let's get cracking. We look at our expected value, and the first thing I'm going to do is test a number that is, yeah, probably a couple less than that. And I'll find out what I've got, and then I'm going to keep going until I reach a probability that is less than 5%, less than 0.05. So we go to our binomial distribution again, we set it up, we've got our x value of 10 here, our n is 40, and our p is 0.3. And this probability comes out at 0.3087 to 4 decimal places, which isn't less than 5%. That's our number that we're comparing with. Okay, so it's not less than 5%, so we have to keep going. 10 is not significant. Let's try 9, and we get 0.1959. Again, isn't less than 5%, so we have to keep going. Let's try 8, and we get 0.1110. It isn't less than 5%. So we're going to have to keep going. And the message here is you just keep going until you get a result that makes sense. So we've got 7, 0.0553, definitely closer, okay, but still above 5%, 5.53%. We need it to be 5% or lower. So I've got a feeling here that we're going to get to 6 and we're going to get our answer 0.0238. Again, all to 4 decimal places. So this one here, less than or equal to 6, that is our critical region. So we can write two things about this. We can say that the critical value is x equals 6. That's our boundary. Anything above 6 returns a non-significant result. Anything less than or equal to 6 returns a significant result. So that means that our critical region is x is less than or equal to 6. So in this circumstance, out of this sample of 40, anyone who any number of people who choose starters that is 6 or lower is evidence that the probability is less than 30%. So We have here on one day 7 order a starter. So what we're looking at here? 7 is not inside the critical region. Okay, 7 is not less than or equal to 6. And that means that 7, although it may look significant, is not significant. So 7 isn't less than or equal to 6, and we know from this it has to be less than or equal to 6 to be considered significantly lower than 30%. So 1 is that this time there is insufficient evidence to reject H0. So the language is almost identical. Whereas in the previous question we had sufficient evidence, we could reject it. This time we have insufficient evidence to reject H0. And part 2, we're going to put the claim, the answer in terms of the context. And we're going to say no evidence. That's not how you spell evidence. There we go. No evidence that the proportion of customers who ordered a starter. Now don't skimp out on this. You need to write out the full conclusion. Has decreased. And there we have it. We did our hypothesis test by setting up our hypotheses and our expected value. We tested some values until we got one that was less than the significance level. And then we made a conclusion based on that. Now let's have a look. I like this part C, this last part of the question. State the conclusion you would have reached if you tested at the 10% significance level. Well, what does that mean? The 10% significance level means that when we were looking at these probabilities, we would keep going until we found one that was less than 10% rather than less than 5%. And actually what you can see is if we had tested less than 10%, then our critical region would have been less than or equal to 7. So I can say CR for critical region would have been X less than or equal to 7. And how would that have affected our conclusions? Well, we actually had 7. So 7 this time is inside the critical region. And our two conclusions would have been different. They would have been sufficient evidence to reject H0 and we would have had there is evidence that the proportion of customers ordering a starter has decreased. All right, so that tells you how the significance level has quite a lot of power. But also, in the first part of the question, we could say statistically that there's a 5% chance that our answer is wrong. In fact, we could say that there's a 2.38% chance that our answer is wrong, but we'll get to that in another lesson. However, for part B, if we change it to 10%, then we're basically saying that there's a 10% chance that our answer could be wrong. So the smaller the significance level, the more trustworthy your conclusion is. Okay, time for a final example. What I want you to do is pause the video and have a go first, and then watch me work through it. So we have, again, past records this time from a supermarket that showed 20% of people who buy chocolate bars buy the family size bar. On one particular day, a random sample of 30 people was taken, and 2 were found to have bought a family size bar. And then test 5% significance level again, whether or not the proportion had decreased. State your hypotheses clearly. Now, you always have to state those clearly. So first things first, hopefully you're getting into the rhythm of these now. Binomial distribution. We have a sample of 30 people and our probability is 0.2. Both of them taken from the question. Our H0 is that yes, the probability is 0.2. There's nothing to defend. Everything is as it should be. But our alternate hypothesis is again that the probability has decreased. Our expected value in this particular question, so out of 30, how many would you expect to have bought the family size bar? You'd have expected 6 with a probability of 0.2. We have a 5% significance level again, and our test is one-tailed. So let's set about finding our critical region. We'll go, again, a couple either side of the expected value. So we'll go less than or equal to 4. And again, that's just a starting point. It's not a set in stone rule. It's just to save me writing out lots of extra working. So let's test that. Binomial distribution on the calculator again. This time x is 4, n is 30, p is 0.2. So we have 0.2552. So that is bigger than 5%, so we keep going. Let's go back and change that to 3. 0.1227. Again, bigger than 5%, but we are getting closer. Change it to 2. 0.04418. 442. Again, all of these to 4 decimal places. And we have found one that is less than 5%. So we have a critical value of x equals 2. That was the first result that gave us a probability less than 5%. And we have a critical region where x is less than or equal to 2. How do we use that information? Well, on one particular day, 30 people were sampled. 2 of them were found to have bought a family size bar. So 2 is our test statistic. That's what we're checking against. And we can say that 2 lies inside the critical region because 2 is less than or equal to 2. And remember what that means. It means that any result that is less than or equal to 2 is significant. It returns a probability less than 5%. So conclusion 1, there is sufficient evidence again to reject H0. And conclusion 2, there is evidence that the proportion of people, and again I'm using the language from the question here, the proportion of people who bought a family-sized bar had decreased. And like I said before, don't skimp out on your conclusions, okay? You do need to write those 2 sentences. It is about as close as you get in A-level maths to writing an essay, okay? And that's it. So hopefully you were able to do that without looking back at the video. But if not, don't worry. Our second lesson this week, where you will be in, we'll talk about finding greater than probabilities, but we will have time to practice this skill as a whole. And remember, we have 2 weeks on hypothesis testing. So certainly by the end of that time, you will be fantastic at it. Okay, I'll see you in class. Thank you very much for watching.